Hello guys, what's up? I am engineer AK and today we are going to study the fifth lecture of the chapter 2, metal structure and crystallization, and it's one of the most important topic of this chapter. So let's get started. So what is crystallographic plane? The layer of atom or planes along which atoms are arranged are known as crystallographic planes. And the points are, let's suppose in this diagram you can see there are points, right? These black dots, these are the points. These points are called the lattice, as we have studied before in the topic of crystal structure, right? And the arrangement of atom on lattice, so crystal, okay. And if on these point, like these black points, if I set atom here, one atom here, like let me show you, right? So if here I place atoms on these points, right, these are the lattice, and if on this point I place atoms, and so a crystal will be formed. Okay, like these are the lattice points, right? These black dots, and if I place atoms, like if I place here these green one, if I place their atoms, so it become crystals, right? This is how crystal form. And we take different crystal plane, the crystal plane link the atom, okay. And these are the planes, right? These let me change the color. Let's take this blue one. Okay, here we go. So these, if we join the atom, so it give us a plane. It is a plane, right? This is a plane, this is another plane in different direction, right? This is another plane in another direction, and same with the case these one. So these are crystallographic planes, right? Okay, let's move further. Now the second topic is it is the most I would say the important topic of today's lecture, Miller indices. So what is Miller indices? As we have discussed that what are the crystallographic planes, so there should be something or any technique or any way in order to study this plane. So Miller indices is used to study this crystal plane and to get all the detail of the plane, right? And all the parallel plane will show same result. Mean like these green one, if we see this green one, right, so these are parallel to each other. Same if this purple, if I talk about this purple one, so these are also parallel, same these red. So if I find the Miller indices of this one plane, this one, so the plane parallel to this plane will be having the same detail or will having the same results, right? The Miller indices of this plane, this one, this one, this one, this one, and so on, all the parallel plane will give same Miller indices, right? So in order to study if we study the only one plane, so all the planes parallel to this plane will be having the same results, right? Or will give the same details, right? So there are some steps in order to find the Miller indices. The first one is select a crystallographic coordinate system with origin not on the plane. Let's suppose if I talk about this one, like this red one, right? Let me show you. So if I talk about this red one, right, so I cannot take origin here, right? I cannot take origin here, I cannot take origin here or here. I have to take origin somewhere here on coordinates, right? We cannot take like on this plane, like I am marking it. I cannot take plane or on either on this one, nor on this one, the upper one, right? You have to take some at crystallographic coordinate system with the origin not on the plane. We cannot, like, this is a plane, right? This is a crystallographic plane, and how this plane is met, let me show you. Okay, so here is an atom, right? Here is another atom, right? Here is another, and this one is as we have studied before, that when the crystallographic when these atoms join together, like I have told you before, let me show you. Look, when these the crystal plane links the atom, right? It linked the atom. You can see that if I place here atom, so it linked the atom. So same, we have atom here at this corner, at this corner, at this corner, at this corner, so it join it. So you cannot take origin at the plane, okay? You have to take it somewhere at this coordinate, right? Find the intercept along in the term of the respective lattice parameters, or take intersection. Then you have to take intersection. Like if I would say this is origin, right? And if I'm talking about this red one plane, right? So we can see that it is intersecting the x. Okay, you have to take this distance of the cube as 1, right? 1, this one is a 1. We are taking this magnitude as 1, okay? You have to consider it, right? Like I would say that this cube has a magnitude of 1, right? So if we can see, so if I am taking from this origin, so we can see that at x-axis the plane is cutting at 1, right? If I see at z-axis, so the red plane is parallel to the, like the red plane is parallel to this line. It is not intersecting or cutting this plane, right? And if I am see at y-axis, so at y-axis also this plane is not cutting, right? The y-axis cutting the yellow plane, and the z-axis, at z-axis it is cutting the green, not the red one, right? So you have to find the intersection. Then after finding the value, you have to take the reciprocal of it, right? And convert into the smaller value if needed. Like for example, if I say the Miller indices comes out 222, so you have to convert it to the least value, so you can divide all those by 2, so it will give 111, right? Or writing the value in small bracket or parenthesis will be the Miller indices, right? So it's the way how you find the Miller indices. So let's show this simple example, so you will understand it, that how it works. Okay, so now I want to find the Miller indices of this red one, right? So if I am taking this is as my origin, right? So at x-axis it is cutting at 1, right? Okay, here I have written already, right? 1. Oh, and yeah, HKL XYZ can also be represented by HKL, okay, small l. At z-axis it is cutting it at infinity, right? Because it is not cutting because this plane is parallel to this z-axis, right? So I am taking it as a infinity, or sorry, z-axis, this one, right? And same if I see it at y-axis, so it is also parallel. It is not touching this red one, so it is also at infinity. So 1, infinity, and infinity, right? So the second step that I have mentioned here was to take a reciprocal, right? So here I have taken the reciprocal of this one, so 1 over 1, 1 over infinity, and 1 over infinity. So 1 over 1 give 1, 1 over infinity gives 0, and 1 over infinity gives 0, right? So the Miller indices is 1 0 0, right? The Miller indices of this red plan. Now let's see some other examples so you will betterly understand that how it work. Okay, let's take this example, right? So let me change the marker. Okay, now this one, yes, this one. So let's suppose I am taking this as origin, right? So if I move in x-axis, so it is parallel to this point and it is infinity, right? If I move at y-axis, so it is again not touching the blue, like it is not touching this plane, right, that we are going to find its Miller indices. So again its y-axis is infinity. But if I see at z-axis, so it is cutting it at 1, so 1, right? Now taking the reciprocal, right, 1 over infinity, 1 over infinity, and 1 over 1. 1 over infinity gives 0, 1 over infinity gives 0, and 1 over 1 gives 1. So its Miller index is going to be 0 1 1. Let's see, right? 0 1 1. Oh, sorry, 0 0 1, right? Now let's see in another example here. Example 2. Let me, yes. So here again I am taking this as origin, right? So if I move an x-axis, so it is cutting it at 1, right? Here I have mentioned it. If I move at y-axis, so it is parallel and it is not touching each other, so I would say it is meeting at infinity. And same with the case here, infinity. So 1 at y-axis infinity, at z-axis infinity. Now taking reciprocal of it, right, so you will get 1 0 0, and its Miller index is 1 0 0, right? Let's moving toward another example. Okay, okay, so again I am taking this as origin, right? So if I move in x-axis, so it is cutting it at infinity, I would say. If it is moving at y-axis, so we can see that it is cutting it at 1, mean from here to here at 1 distance, right? It is, I told you, it we have to take it as 1, right? So it is cutting the y-axis at 1, and at z-axis again we have infinity, right? So at x-axis infinity, at y-axis 1, at z-axis infinity. Now taking the reciprocals, 1 over infinity, 1 over 1, 1 over 1, so we get 0 1 and 0, right? So its Miller indices is 0 1 0. Now taking another example. Okay, hold on. Now it's okay, let me make it a bit lower. Okay, now in this example again, if I am taking this as origin, right, so if I see at x-axis it is cutting at 1, right, as I write here 1. If I move at y-axis, so it is cutting it at infinity, right? They are not touching but they are parallel to this. And if I move at z-axis, so it is again cutting it at 1, right? So at y-axis infinity, z-axis 1, taking reciprocal, 1 over 1, 1 over infinity, 1 infinity, so 1 over 1 1, 1 over infinity give us 0, and 1 or 1 1, so it will give 101. Let's see. 101, right? Its Miller indices is 101. Now taking example 5. Now again you have to take origin. At x-axis it is cutting at 1, right? Here you can see the plane is cutting, it's cutting the plane. And if I move in y-axis, so again it's cutting this plane, right? That is at diagonals, right? That is again cutting at 1. And if I move at z-axis, so it is parallel to this plane and not cutting it, so infinity. So at x-axis 1, y-axis 1, and infinity, taking its reciprocal, step 2, right? And we get 1 1 infinity, 1 1 0. So here we go, 1 1 0, right? Let's now see this example. So here we can see this is the origin, right? If I move in x-axis, so it is not cutting it, so I can take it as infinity. Now if I move at y-axis, so yeah, it is cutting here at 1, right? And if I move at z-axis, so yeah, again it is cutting here, so it is 1, right? So infinity 1 1, taking a reciprocal of it, 1 1 infinity, 1 1 1 1, so it will give 0 1 1, right? So its Miller indices is 0 1 1. Now taking example 7, I am taking as much example because it is important. So the more you will practice it, so the more you will get the idea and will be able to find Miller indices of different planes, right? So in this case, again taking the same origin, yeah, at x-axis it is cutting it at 1, right? If I move at y-axis, so it is again cutting at 1. And if I move at z-axis, so it is again cutting at 1, right? So 1 1 1, taking as reciprocals, and we will get this 1 1 1, right? Now taking another example of different case. So here again I am taking as, okay, let me change the pen here now because it will not visible here. Okay, so again I am taking this as origin. Now I told you from here to here it's 1, right? But in this case it is half. It is half because it is cutting it at 1 or 2. It is not cutting it at 1, but at the mid you can see here it is cutting it at 1 or 2 at x-axis. If we move at y-axis, so it is cutting it at infinity, right? And if I move at z-axis, it's again parallel and not cutting it, so infinity. So 1 over 2 1 over 2 1 over 1 over 2 infinity infinity. And if I am taking reciprocal of it, so it becomes 2 0 0. Now I have told you you have to reduce it to the least number, so you will divide this by 2, you will divide this by 2, and you will divide this by 2, so it will cancel out and it will give 1, it will again give 0, and this will again give 0. So its Miller indices will be 1 0 0. Let's see. Miller indices 1 0 0. It reduces to simple form by dividing by 2 all numbers. So that's it for today.